Right, today's video is limits to forward speed. Very important for anybody who flies a helicopter, essentially, because it lets you or helps you understand how fast you can go and what your limits are, and essentially what's going to happen if you exceed those limits. All helicopters have a V&E of some kind, and hopefully this will help you understand what could go wrong, why it goes wrong, and how to fix it when it does go wrong. All the usual references, and again, all publications pretty much give the same things. So limit forward cyclic, the simple one, the easy one to start off with, and pretty self-explanatory. So as we go forward on a helicopter, in order to make the aircraft go forwards, we push forwards on the cyclic. That tilts the disc forward and essentially gets that total rotor thrust pointed a little bit more down towards the horizon, which starts to drag the aircraft forward. As the speed increases, we get a flat back, and to counter flat back, what we have to do is to push forward on the cyclic a little bit more. Speed increases again, we get a little bit more flat back, so we have to push the cyclic forward a little bit more. This continuous edging of the cyclic forward means that eventually we're going to get to a speed where the cyclic has hit its furthest mechanical stop, and it literally just cannot go any further. So it doesn't need much more explanation than that, other than that it is a mechanical limit in the linkages. You can draw a picture if you really feel the need to, but it's really not necessary. So that's the first one. So the best way to demonstrate these as we go on and build them is using a top-down picture of the rotor disc, and you can start to annotate on them where these different limits affect. Okay, so I've used a counter-clockwise rotating helicopter head. So we've got a look down basically on the top of the disc here, and the rotor blades are rotating in this direction. So limits to forward cyclic, we generally speaking are going to annotate it onto the actual picture. And that's the easiest way to do it. Okay, so the second limit. Compressibility. Okay, so we're going to take this rotor blade, which is essentially the advancing side blade, and we basically just assume that it's moving around counterclockwise. Generally speaking, rotor blades will rotate at about 300 RPM. You can find out the exact RPM of your particular helicopter, and then if you've got the radius or the blade length, you can also work out the distance that that blade travels depending on which part of the blade you look at. So for example, if we look at the blade tip, in the circle that it travels here, it's travelling a much larger distance than the root. The root of the blade is going to be travelling a much smaller distance every rotation. So when we think about how many times it's rotating in a minute, 300 times, in that minute the tip is going to be moving at a much greater speed than the actual root. So we can actually work that out sometimes, and for this particular demonstration, we'll just assume that the tip is creating an airflow of 400 knots. And as a rough working, we'll just assume that the root is only going at 100. So just in the hover, that's how fast those positions on the blade are moving relative to the air around it, and therefore they're generating that sort of amount of airflow. Okay, now let's bring in forward speeds. Let's say we've got a excessive forward speed. That's going to be generating an additional airflow. And if we just assume that we have managed to get ourselves up to 150 knots. So you can see now the combined speeds here take the root of the blade experiencing a relative airspeed of 250 knots, and then the tip is now experiencing a relative airspeed of 550 knots. So 550 knots doesn't seem a huge amount when we consider that the speed of sound at the sort of international standards is around about 661. So why do we hit issues with compressibility? Well, thinking back to your basic aerodynamics, if we get an airflow over the wing, as it goes over the top of the wing and the longest distance, it essentially has to increase its speed. So even though the relative airflow over this blade is only at 550 knots, what we can find is that at some point over the top of the wing where it's actually sped up, we might actually find that the airspeed increases to above 550 knots. In fact, it's highly likely to. The other thing to then add in there is once we start to get a little bit faster over the top of the wing and we start to move towards the speed of sound, the molecules in the air do start to experience compressibility. So they actually start to get pushed a little bit closer together. If you push them closer together as well, the local speed of sound in that area also comes down. So the local speed of sound at the top of the airfoil there might not actually be 661 knots, it might even be less. This isn't hugely relevant at the moment, and we can just assume that the speed of the airflow over the top of the wing has approached the speed of sound. If it does approach the speed of sound over the top of the wing, then essentially along with compressibility, you're going to start to form a shock wave. It's not really in the scope of this video to sort of examine the different types of shockwave, and you shouldn't really try and delve into that too much. Okay, so it doesn't matter whether it's oblique or normal or any of the other aspects of it that go into shockwave and supersonic transonic flight. You just need to state that you get a shockwave on the top. When we get a shockwave, what essentially is happening though is the air molecules inside that shockwave are slowing down very, very quickly. And essentially what you get behind the shockwave is a rapid slowing down of the air and also an increase in pressure. What does that do? Well, we essentially end up with that annoying situation where we get high pressure at the back, low pressure at the front. There's a lot more complexity to this, and I've just generalized it a little bit to make it simpler to understand. But the main thing to take away is that when you get the shock wave, you get a considerable amount of wave drag, you get a considerable amount of drag, and as you can see also, if you've interrupted that boundary layer and you've interrupted the airflow over the top of the wing, you've also lost lift. So what does this do? So if you've increased the drag and you've reduced the lift, you've changed the lift drag ratio, and so what happens to that blade is it starts to experience a dissymmetry in its lift. So you're going to get all sorts of effect from that. You're going to get buffet, you're going to get definite control response changes, and also what you'll notice is that the center of pressure of that blade has started to move slightly more to the rear, so you'll get more pitching moment on that blade. There are a number of factors which have been introduced to helicopters to sort of try and counter this. They've tried to make the blades a little bit more sleeker. If they make the blades sleeker, then you don't experience quite the same amount of increase in speed at the top. And there's also issues you get, or benefits you get, from a slightly sharper leading and trailing edge. And in addition to this, you'll also notice on most blades these days you get either a burnt tip or a swept tip. And the idea behind that essentially is if you have a swept tip, then it reduces the speed or the relative airflow that's going over that tip. Again, I'm not going to go into that right now, but it essentially reduces the speed over the tip. If you reduce the speed over the tip, then you won't get, or you're less likely to get towards your local speed of sound, and you're less likely to hit your critical Mach number. So that's the compressibility effects, and that's the limit that you'll get from forward speed there. So the next two are probably the most important ones then, and they are intrinsically linked. So airflow reversal. So we're looking now at the retreating blade coming down on this side, and so this is the retreating blade. It's moving in this direction, but the aircraft is moving in that direction. So first of all, what we are doing is we're creating an airflow by moving the aircraft in this direction. But at the same time, by moving the aircraft in the opposite direction, we're creating an airflow which is counteracting our generated airflow. So again, we'll just take some arbitrary figures. If we assume that we have created a .400 knots airflow on the tip, and we assume that we have created .100 knots at the root, but then we push the aircraft forward at 150 knots, we can now see that we've got a resultant airflow of 250, because this forward movement of the aircraft is cancelling out a little bit of this 400 knots that we've created by pushing the blade forward. So we're only getting 250 knots up on the tip, and unfortunately we're actually removing completely our generated airflow over the root, and we're replacing it with 50 knots that's moving in completely the opposite direction. So we get negative 50 knots. What does that look like? Well, we end up with a flow pattern which, as we move towards the root, literally sees the airflow reverse direction. What effects does this have? Well, first of all, clearly we've lost all of the lift at the root, so we're no longer generating any lift at all, because the airflow is now travelling from the trailing edge to the leading edge. So thinking back to basic aerodynamics, we're no longer creating lift at all and not getting that the correct change in pressure on the top and the bottom surface. But as we go out, we can also see that we're gradually increasing the amount of lift that we produce. However, at 250 knots, when you think about the lift equation and the fact that it is proportional to v squared, clearly we're producing substantially less lift. So therefore, if we're producing less lift on the retreating side, what's going to happen? Well, it's going to drop down. It's going to flap down. And in order to stop the aircraft from rolling over to the left, we have to put right cyclic in. But as you can see, the faster you go, this area of reversed airflow is going to slowly move out further and further and further until we aren't producing any lift on the retreating side blade at all, and the whole aircraft will just continue to roll to the left until we run out of right cyclic. So retreating blade stall, you'll often see this as RBS, but retreating blade stall comes about towards the end of airflow reversal. So we already talked about the fact that as we slowly start to lose lift down towards the tip of the retreating blade, we need to do something about it. What do we do? Well, we put right cyclic in, and that right cyclic essentially will increase the pitch on the retreating side in order to try and lift it up. However, again, going back to basic aerodynamics with a fixed wing, we are eventually going to get to the point where our airflow is quite slow, and we're eventually going to reach the point where we hit our critical angle of attack. And our critical angle of attack is the point at which we start to stall. And the airflow is quite literally coming over the top of the blade and then starting to stall, because we put so much right cyclic in to try and generate enough lift on the retreating side due to airflow reversal. And now we're starting to find that we're getting a stall occur because we've reached our alpha critical, or our critical angle of attack. So what happens when the blade stalls? Well, when the blade stalls, it starts to drop because we've lost lift. And this further exacerbates the problem, because as the blade now starts to drop, we've already talked about the fact that it flaps down over here. Well, if the blade is now stalled, it starts to drop a bit more. And as it drops, it generates itself a rate of descent flow. And that rate of descent flow adds to whatever airflow is left remaining, or rotational airflow we've got. And as you can see, that further increases our angle of attack, which just further stalls the aircraft. So the problem, as you can see now, once you go through airflow reversal out the other side into retreating blade stall, is you get a gradually exacerbating effect. And any kind of corrective action in terms of right cyclic is actually only going to make the problem worse, because you're going to continue to stall the blade more. So where are all these going to take effect? So again, you need to break them down one by one. First of all, compressibility. We already talked about it's predominantly around the advancing side, and the position where the advancing side is experiencing the most amount of airflow at the tip is going to be around about the 90-degree point, and we generally speaking see compressibility effects in this sort of forward right quadrant. Airflow reversal. So airflow reversal we already talked about. Again, we generally see it in the retreating side, in the vicinity of the root, and again that slowly spreads out as you move faster, but the initial phase we like to see it retreating side once we get to the area of the fastest movement of air. So that's going to be at the 90-degree point again, when the blade is perpendicular to the oncoming airflow. So the last bit then, retreating blade stall. So generally speaking, we're going to see that as soon as we get to the 90-degree point again, and we're going to see it gradually increasing as it comes around the corner. Importantly to note there though, you can see that just like the compressibility, we're experiencing the retreating blade stall at the tip. And the reason why we're experiencing it at the tip, even though we've got washout, so we've got a higher pitch down near the root than we do at the tip, so you'd think that this bit would stall first. Well, first of all, that's not producing a lift anymore anyway, but also, as we've already talked about, because the blade is flapping down, because we're constantly losing lift as it comes through this 90-degree point, because it is flapping down at that point as it loses lift, it's generating this rate of descent flow. Because the blade clearly is going to be travelling vertically, it's going to be travelling at a greater distance at the tip than it is at the root. Thinking about it logically, if this is the mast here and this is the tip, if you look, if it flaps down, the tip is moving all the way from there to there, so that's quite a considerable distance, whereas the root is only moving half the distance, or probably about a quarter of the distance. So the fact that it's moving that much further means it's generating that much more rate of descent flow. If it's creating more rate of descent flow, then generally speaking, the relative airflow is going to be made a little bit steeper, which is going to create that critical angle of attack a little bit earlier. Okay, so the last thing we just need to look at then is how we can tell we're getting into this awkward situation. So for rotating blade store, as you can see, just like you would in a fixed wing, if we start to get separation off the top of the aerofoil, then we're going to start to experiencing changes in lift and additions in drag, so we're going to get a bit of buffet. We're also, as you can see, if it's the blade is stalling over at this side, it's going to be flapping down, and if it's flapping down over here, we're going to get a little bit of a roll to the left, but as you can see, it's going to continue flapping down to its maximum point of flap down at the rear, and so we're going to get a bit of pitch up. And then clearly combined with both of these two, the pitch up left roll and the loss of lift overall, if we do lose the lift on that side, then we're going to start to lose control. Most likely just experienced by sluggish response. So they're the bad parts. How can we get out of it though? Okay, so first of all, we've talked about the fact we are increasing that pitch angle to the point where it's stalling. So clearly the first thing to do is to lower the power or lower the collective. That's going to reduce the pitch, and it's going to start to reduce the stalled region. Reducing your speed stops all of this again, so if you can lower your power and also reduce your speed in any way, that's going to have a similar effect. Reducing the severity of the manoeuvre. Again, high energy or high dynamics in the manoeuvring is going to cause random excessive airflow, and again you're more likely to experience that flow separation. So where's the really bad bits where we're likely to see this then? So probably the most important thing to think about here high speed, clearly, but also high DA. Okay, so high DA, high all-up mass, all of these areas are going to affect the amount of lift you need to produce, and also they're going to affect the lift equation. As soon as they affect the lift equation, that's when you're going to need to add either more power, more angle of attack, or more lift. And lastly, turbulence. Turbulence, if you're travelling at relatively high speeds and you've got relatively high turbulence, you're affecting the airflow over the whole of the disc at different areas, and you're more likely to either exceed the speeds at various points or experience flow reversal. So that's pretty much concludes the whole that you'd need to put on there. Like I said, try not to start delving down too many rabbit holes, especially when it comes to compressibility. As always, if you have any questions or points or criticisms, don't be afraid to put them in the comments below, and I will endeavour to change it. Thank you very much indeed.